So in the last video, we saw how to measure algorithms efficiency. We saw that if an algorithm's efficiency is like represented by T of n, then this T of n is basically measured using the order of growth of that particular algorithm's basic operations count, C of n. Now we saw the importance of order of growth in order to like measure the algorithm's efficiency, but how do we denote how efficient the algorithm is? So in order to like denote the efficiency of algorithm, there are some notations which we use. So these notations are actually asymptotic. So in mathematical terms, asymptotic is something which actually approaches a value or a curve arbitrarily like closely, but it never touches that curve. So if if I say the line is like asymptotic, this usually means that there is some curve. This line would actually approach this curve, but it would never touch it. So that is what asymptotic usually means in mathematical language. So we use some asymptotic notations to denote how your algorithm's efficiency is. So there are actually three notations which we use. One is called the big O notation, usually represented by O of n. Then there is something called big omega, so big omega of n, and then there is big theta. We represent it using theta of n. So these are the three notations using which the algorithm's efficiency is usually denoted. Now, if we want to see how the algorithm's efficiency is, then we should basically have some other function to compare it with. So if t of n is our algorithm's efficiency, then we would basically need one more function. Let's call it g of n. So this g of n would be some function with which this algorithm's efficiency would be compared. So let's talk about these three notations using g of n and t of n. So let's start off with some informal definitions just to get a hang of it, and then we'll move ahead with the formal definitions. So if we want to speak about the informal definitions, so let's talk about big O of n. So big O. So if let's say since we are comparing it with this function g of n, so big O of g of n, it usually if you want to like describe it informally, this means that this should be a set of functions. So this should always return a set of functions. So this should be a set of functions which should basically have like either the same or a lower, same or a lower order of growth. Okay, order of growth as g of n. So big O of g of n means it is a set of functions. All these functions would basically have same or lower order of growth as g of n. Now, if g of n was, let's say, n square, then everything which is under n square would be included in this set of functions of big O of g of n. Like for example, n, and then maybe log n. All these are under n square. And even let's say n square by 2 would also be same, because it is again same or lower. So this is how we informally define. So all the set of like a set of functions having same or lower order of growth as g of n, that would be denoted using big O of g of n. So similarly, if we want to talk about big omega, so big omega of g of n, so this should be a set of functions again. So this should have same or higher order of growth as g of n. So for example, if we consider g of n as n square, then big O of g of n might include n square by 2, it might include n cube, it might include n factorial. So all these have a higher order of growth when compared to g of n. So this set would be actually big O of g of n. Now there is one more which we saw, big theta. So let's see the informal definition of big theta as well. So big theta of g of n would actually again be a set of functions. So these functions would have the same order of growth as of g of n. So again, if we consider the same example, g of n is this, then big theta of g of n would be like, let's say, n square by 2 or n square plus 2. So something like these. These would belong to big theta of g of n. So these were some of the informal definitions. So big O of g of n would be having a set of functions which have either lower or same order of growth as of g of n. Big omega would have all the functions, a set of functions which have order of growth same as g of n, or it would be higher than g of n. And then big theta would have the same order of growth as g of n. So these were some informal definitions. Now if you want to talk about the same thing formally, so how we would define big O of n is like, so since we want to talk about the algorithm's efficiency, so t of n, we will say that this function, so a function t of n, it is set to be in g of n. So we will denote it as this, so big O of g of n. We say that a function t of n is in big O of g of n because this is a set of functions only if this t of n is like bounded. So I'll just write it down, is bounded above by, let's say, some constant. It is bounded above by some constant multiple of the function whatever we have, that is g of n. And this should be the formal definition of big O of n. So whatever a function t of n, so here t of n is our algorithm's efficiency. We say that it is in big O of g of n in this set of functions only if t of n is bounded above. So it is like, it is bounded above, so there is a limit above which it cannot go. So it is bounded above by some constant multiple of this function. So if, let's say, there is some positive constant c and there is some positive integer n0, so we would basically say that t of n would be less than or equal to c times g of n because it is bounded above by some constant multiple for all the n's which are greater than this, greater or equal to this positive value n0. This is how you would basically define more formally. Now if you were to like plot how the big O of n graph would look like, so let's say our function, so since we are comparing, let's say g of n is some function g of n. Now big O of, I mean t of n, if it is in big O of g of n, then in that case this t of n would approach g of n but would never touch it. So this is how big O of n would look like. So this is big O of n. So similarly, big omega of n, we know that this includes a set of functions having higher or same order of growth as of g of n. So it is again like we would say that t of n would belong to big omega of g of n if t of n is bounded not above but it is bounded below now. It is bounded below by some constant positive like multiple of g of n. So again here it would be like t of n is greater than or equal to a constant multiple of g of n. So this is for big omega. Now if you want to talk about big theta, and like the graph would for big omega would be like, so if you have, let's say, let's take another sheet. So for big omega, so if let's say this is our function g of n with which we are comparing an algorithm's efficiency, g of n would be like, big omega of t of n would be something like this. So this is our big omega of n. So it is bounded below by some constant multiple of g of n. It would approach this function but it would never go below this. This is big theta of n. Now we can also formally define big theta. So this would be like, we could say that t of n belongs to big theta of g of n if it is actually bounded both above and below by a constant multiple of g of n. So since it is having same order of growth as g of n in case of big theta, if let's say this is g of n, then theta would actually, so this is our t of n. So this should be our t of n. So these to be g of n. So in this case, we say that t of n is actually going to be bounded above and below by some constant multiples of g of n. So t of n would actually be bounded both above and below by some constant multiples of g of n. This would be having same order of growth as of g of n. So this is big theta of n. Now usually, like while denoting the algorithm's efficiency, we usually use big O notations, but you are like free to use the other two notations as well. So there are some basic efficiency classes which everyone should be aware of. Like the first one is the constant class. So this is like 1. So we just say big O of 1. So this is the best class, best case efficiency. Then you have like logarithmic, which is log of n. Then you have linear, which would be n. You also have linear arithmetic, which is like n log n. Then there is quadratic, which would be n square. Then you have cubic functions, n cube. Then you have, let's say, exponential. This would be 2 power n. Then you have factorial. This is like n factorial. So if you just look at the order of growth of these, this would be like increasing in this way. So if you just put some n value as 1, you can just calculate these. You'll see that always the order of growth of these values, n factorial, if it is, let's say if you put it as 2, 2 factorial is like 2 times 1. So, there would be some limit after which it would go. So, if you just, let's say, you put some huge value for n. So, since as n grows, how these functions would grow, that matters. So, if n is like, let's say, if you put n as some 100 and calculate all these values, then you'll see the order of growth for n equals 100 would be like much higher for the ones below than when you compare it with the ones above. So it will like increase basically. So these are some of the basic algorithm, classes which you should be aware of. So that's it for this video.